Alright, so we are moving forward a little bit with probability, and basically what we want to do is just talk about some different ways that we can use our basic knowledge of probability to answer problems. So here's one of the things that we need to consider. When we look at an event that's happening, or two things that are happening, we need to know, are they independent events or dependent events? And I've used those words before in this class. Okay, independent means you can do whatever you want, right? You don't care at all about what's happening with the other one. So for instance, if I roll two dice, two six-sided dice, and each of them has a 1 in 6 probability of getting a 3, then I want to know maybe what's the probability that whenever I roll those two dice I'll get 2 3s. Well, if one's a red die and one's a blue die, for instance, does it matter what happens on the red die? No, the red die, whenever I roll it, it's completely independent of what's happening with the blue die over here whenever I roll it. Now that's assuming that, we're not bumping them into each other or something weird like that. So these are 2 or more occurrences whose outcome does not rely on the outcome of the other. Oops, I can't write today. Outcome of the other. Okay, so 2 or more occurrences whose outcome does not rely on the outcome of the other. Okay, so in other words, when I find the probability of A, some event A happening, it is not dependent on the probability of whatever occurrence is happening over here with B. So if one outcome happens, okay, that has nothing to do with the other outcome. Okay, so in other words, well, let's do the one that I just talked about. So let's say, example, you have a red and a blue six-sided die. Okay, and we're going to say that these are fair dice. Now, what does that mean? Remember, we talked about fair whenever we did the intro to basic probability. So, in other words, when I roll this die, it has just as equal of a chance of rolling a 3 as it does of rolling a 5. So all of the sides are weighted equally. We do not favor one side over the other, right? So make sure these are fair dice. The opposite of that would be loaded dice, right? Like if somebody has a pair of dice that when they throw them, they always come up with double ones, okay? Snake eyes, they call it. Okay, so if that happens, and it always comes up that way, or most of the time it comes up that way, then that's not a fair set of dice, okay? So you have a red and a blue six-sided die. Find the probability that you get 2 3s. Okay, so a lot of times we'll say probability that you get a 3 and then another 3. So the red die is a 3 and the blue die is a 3. Okay, well, let's think about that. What's the probability that this first die is a 3? 1 out of 6, right? Probability that the red equals a 3. 1 out of 6. Okay, what's the probability that the blue equals a 3? Also 1 out of 6, right? So individually, these events occurring, okay, the red's a 3, the blue's a 3, individually, they have a 1 in 6 chance, and you could just divide that out and figure out what that percentage is if you wanted to, okay? But the problem is, what about together, okay? And there's something called the counting rule for outcomes. So the counting rule says, if these events are independent, which is why we started with that definition, independent events, then you can multiply the probability of A times the probability of B. Okay? And that's how we can find out the combined probability. Okay, so that's the probability of both of those things happening at the same time. Okay, the combination. So, all right, so let's look at that. What would that be then? Okay, well, the probability of A times the probability of B, we said in this case the probability, if A is, the red is a 3, the probability of that is a 1/6, right? Times the probability of B, we said B is blue, the blue die is a 3. That's also 1/6. Okay, well that just becomes multiplying fractions, and when you have two fractions multiplied together, you just multiply straight across the top and straight across the bottom. So 1 times 1, 6 times 6. Okay, so it's a 1 in 36 chance that I'll get a 3 and a 3. Okay. And in fact, that happens every time I roll 2 dice, right? If I wanted to know the probability that I roll, the red die is a 3 and the blue die is a 5. Okay, so I'm just doing red and blue for whatever reason. Red first, blue second. Okay, so if that's what I want to know, well, what's the probability that the red die is a 3? Well, we already know that's a 1/6. But what's the probability that the blue die is a 5? Well, there's also 1 5 on that die, right? So it's 1 out of 6 as well. So that's also 1 out of 36, okay? As long as these are fair dice, then it remains the same. Okay, it doesn't matter. What if there were 3 dice? Okay, does the outcome of the third die, let's call it the green die, does it have anything to do with the outcome of the red die? So if this is the red and this is the blue and this is the green guy, I roll this die, it's a 1 in 6 chance. I roll this die, it's a 1 in 6 chance. I roll this die, it's a 1 in 6 chance. Yeah, they don't have anything to do with the outcome of the other one, right? So they are independent events, which means what? We just take 1/6 times 1/6 times 1/6, and we multiply that together, and I believe that's 1 out of 216. You can check me. I didn't do the math. I'm sorry. Yeah, so 20. Good. All right, so that's just scratch work. Ignore it. Okay, 1 in 216. So that's what's going on there. It becomes a matter of they don't necessarily depend on each other, so we just find each one's individual and then we add them. That's not always going to be the case, but sometimes it happens that way. Okay? Well, let's talk about something else. So we're talking about multiple events happening, at the same time, so to speak. So let's talk about the probability of having children. Okay? And in general, we just have 2 probabilities whenever we have kids. We have a probability of having a girl or a boy. So whenever you have a baby, those are your outcomes. And we know that more or less, it's like tossing a coin, right? So what's the probability that Susie Q has a boy? Well, there's one option for boy out of 2 possibilities, a boy or a girl, so that's my total. So the probability of having a boy when you're having a single child of a boy with 1 child is 1/2 or 50%. You got a 50% chance. And actually there's a little bit of data going on, a little bit of statistics that have shown maybe it leans one way or the other, boy versus girl, but it's about a 50% chance. Okay, so then what? Well, what if Susie Q wants to have 2 children? Okay, so then we find what's the probability of having a boy and a boy, for instance, or what are all the different possibilities, basically. So we start going, oh, there's lots of different options here. So, well, in general, is the birth of the second child going to be based at all on the birth of the first child? No, one does not depend on the other. They are not rely on it. If you have a boy the second time around, it does not rely on the first one. Now again, there are some statistics that show some people may be more likely to have a boy than a girl or this or that, but in general, the outcome of the second baby's gender does not depend on the outcome of the first baby. So what's the probability that Susie Q will have 2 boys? Well, it's 1/2 times 1/2, right? Because the probability of the first boy is 1/2. The probability that the second child will be a boy is 1/2. Okay, so that's 1 in 4. She's got a 1 in 4 chance of having 2 boys if she has 2 children. Okay, so there's lots of different options going on there. So here comes a little bit more of what we want to do. Here's an example. Suppose a family wants to have 3 children. Okay, and on a test I could change this any way I want. I'm going to introduce a little diagram to us. We're going to see what's going on here. Okay, so when they want to have 3 children, the question that I'm going to ask right now, and then we'll expand this, is what are the odds? What are the chances? We'll say actual probability. What is the probability they have 2 boys and 1 girl? What is the probability that they will have 2 boys and 1 girl? All right, so here's what we're going to do. We're going to introduce a concept. It's kind of a concept map, actually, called a tree diagram. And if you've seen it before, please bear with me. If you haven't seen it before, yay. Okay, something new for you to learn. All right, a tree diagram. So here's the way it works. We have these little nodules, and we're going to talk about what's happening. The first nodule here is going to represent the event that Susie Q has her first child. Okay, and out from that little nodule, we're going to have branches coming out. And we say, well, what are her options for her first child? Well, she could either have a boy or she could have a girl, right? Okay, those are her 2 options. Well, what's the probability of her having a boy? It's 1/2, right? What's the probability of her having a girl? It's also 1/2. Okay, so for the first child, we're good. Now, right in here, after I have the first child, I'm going to talk about the second child. So this next nodule that I make is going to be the second child. Now, I need to branch out from every possibility that we had. So we had the possibility that first she has a boy, so ignore this one down here. If she had a boy first, then whenever she goes to have her second child, what are her options? Well, she could have a boy, and what's the probability of that? 1 in 2. Okay, or she could have a girl, and what was the probability of that? And in my head, I hear you saying 1 in 2. Okay, so that's if she had a boy first, but what if she had a girl first? Well, from the girl here, she could have, her second child could be a boy. What's the probability of that? 1/2. And, or her second child could be a girl. And also, I hear you saying in my head, the probability of that is also 1/2, okay? So right now she's had 2 children. I haven't done the third child yet. She's had 2 children. Let's look real quickly, because we said the probability of her having a boy and a boy, we're going to see how to read this concept map. The probability of her having a boy and a boy was 1 in 4. That's what we said up here, right, for 2 children. Okay. Notice that with my tree diagram, as I go through here, I now have 4 possible outcomes that were 4 paths, okay? This first one is the one we're after, the boy and the boy. That's one pathway, right? Okay. But she could have had a boy and a girl, that's a second pathway. Or she could have had a girl and a boy, that's the third pathway. Or she could have had a girl and a girl, that's the fourth pathway. So there are 4 options here. And you notice whenever you multiply the 1/2 times the 1/2, that gives me the 1 out of 4. There's 1 out of 4 pathways here. So as you read this, sometimes I tell people it might help if you get a marker or a highlighter or something like that, colored pencils, anything that helps you kind of follow it through and see what's going on. So right now, this is the thing that we just said. What if there were 2 boys? Or, yeah, what if she has 2 children? What's the probability that she'll have 2 boys? There's only a 1 out of 4 way that she can do that, right? If it had been, what's the probability she'll have a boy and a girl, if we don't care about order, now that's important, if order doesn't matter, and normally we don't care, right? We're just saying 2 boys or a boy and a girl, we don't care which one's the oldest, then that actually is a little bit different because she could have a boy and a girl, that's one of the 4 paths. Or she could have a girl and a boy. She would have one of each. And that would be a second of the 4 pathways. So there's actually 2 of the 4 pathways where she could have one of each. With the last one being just girl, girl, that one doesn't count, right? So 2 of the 4, what's 2 out of 4? 2 out of 4 is 1/2, right? So the probability of having one of each is 2 out of 4, or 1/2, 50%. So it's actually more likely, statistically speaking, if you just have 2 children, it is 50% chance, half and half, that you'll have one of each. Okay, so there you go. It's more likely that than that you just have 2 boys or just 2 girls. But if it was just same gender, let's do that. Probability of same gender. Okay, well there was one way that they could have 2 boys and there was one way that they could have 2 girls. That's also 2 out of 4 or 1/2, right? So that is the same percentage-wise as one of each. But if I was just looking at 2 girls, that would only be a 25% chance, right? Okay, so that's 2 children, but now I'm right here. I've finished up the 2 children. I want a third nodule. I want to talk about the third child, right? So I need my options for that. Coming off of a boy and a boy, there's 1. Again, we could have a boy, which is a 1/2 probability, or a girl, whose probability is 1 out of 2. Boy, girl, that was one of my pathways coming off of that one. I could have a boy and a girl. 1/2 is the probability for each of them. And coming off of girl, boy, I could have a boy and a girl. Still 1/2 on each of those. And coming off of a girl and a girl, I could have either a boy or a girl. And still equal probabilities, right? It's not necessarily leaning one way or the other. Okay, so if I've got this going on, okay, now with the third child, how many possible ways do I have to have these 3 children? Well, I hope that you see that there are 8 outcomes out here in this final column, so to speak, right? So there's 8 pathways. Okay, and a pathway, again, is just following from one, first child is a boy, second child is a boy, third child is a boy. What's the probability of that guy? This first top pathway, boy, boy, boy. Okay, so what's the probability of boy, boy, boy? Well, what is that probability? Probability of the first one was 1/2 times. Probability of the second one was 1/2 times. Does the gender of the third child have anything to do with the gender of the first child? Well, no, not really. It's still a 1/2, right? And what's 1/2 times 1/2 times 1/2? 1 on the top, 2 times 2 times 2 is 8 on the bottom. It's a 1 in 8 chance. Now notice that there were 8 pathways, and there's a 1 in 8 chance of having 3 boys. Okay. So what we're going to do is we're going to kind of read some of these pathways, and we're going to see what's going on, and we're going to see some of these outcomes may be similar. So let's go back to the question that we asked. Back up here. Suppose a family wants 3 children. What is the probability they have 2 boys and 1 girl? Oh, 2 boys and 1 girl. Do they care what the order is of that? No, they didn't say the girl has to be the oldest or the girl has to be the youngest or anything like that. They don't care. So whenever I start looking at that, don't pigeonhole yourself into that. Order doesn't matter here. We don't care about order. So when I talk about that, it's not going to matter at all. So what I'm going to do is I'm going to make a list of all my outcomes. I'm going to put it on a different sheet of paper here, as according to this tree diagram. So this is my possible outcomes when having 3 children. And all I'm going to do is I'm going to follow the pathway here, okay, each of the pathways. And like I said, sometimes it might help you if you have a highlighter. I'm just going to highlight the ones that we're after here. So we wanted 2 boys and 1 girl, right? But I'm going to list all of the outcomes. So the first outcome here, this top one that we already did, was boy, boy, boy. And I'm going to start abbreviating here. I hope it makes sense to everybody. The outcome boy, boy, boy is going to be BBB, okay? And the second one here, first we have a boy, then we have a boy, then we have a girl. That's the second pathway. You see it? Okay. That's boy, boy, girl. BBG is how I'm going to write that. And just for good measure, I'm going to highlight it to make sure we know that's one of the pathways we wanted. Because we wanted, let me come back here just a little bit, 2 boys and 1 girl. Okay, everybody remember that. So, boy, boy, girl. Okay, that gives me the 2 boys and 1 girl option, right? All right, what are my other outcomes? Let's see. Let's keep on going. Let's try to do it as organized as we can. The next outcome, and I'll put them right here beside, is what if I went boy, girl, boy. Boy, so it's the next pathway. I'm just working my way down. I did this one first, now I'm doing this one, now I'm doing this third pathway. Boy, girl, boy. Boy, girl, boy. That's the third pathway. What do we think about that? 2 boys and 1 girl, right? Let me highlight these guys. This one was 2 boys and 1 girl. And this one's 2 boys and 1 girl. Now in this case, boy, girl, boy. The girl happens to be the middle child, not the oldest, not the youngest, but we don't care because order doesn't matter. Okay? What's the next route, the next pathway? Boy, girl, girl. Boy, girl, girl is what I see. Boy first, then a girl, then a girl. That's my 4th pathway. So I'm going to give you a second. Is everybody okay with that, I hope? I'm going to give you a second to try to follow my pathways and tell me what are the next 2 routes. So you're going to start here with a girl first. We're done with boy first. What if they had a girl for their first child? Tell me the next 2 pathways. Okay, I'm hoping that you put together girl, boy, boy as your first pathway and girl, boy, girl as your, well, it's actually the 5th and 6th pathways, right? Okay, but it's the first pathway whenever you had a girl first, okay? Now looking at those, this top pathway for having a girl first, girl, boy, boy, what do we think about that? I highlighted it. Girl, boy, boy. 2 boys and 1 girl, right? We don't care about the order. All right, so that happened. All right, and then the very last one, let's see these pathways. Let's see if you can do it real quick. All right, I hope you did them really quickly. If not, pause the video, come back. Girl, girl, boy, that's the 7th pathway. And girl, girl, girl is my 8th pathway here, right? And by the way, you didn't have to do boys first and girls second. I just put the boys on top and the girls on the bottom. That was just the way I did it. It's no big deal. But these are my different possible outcomes. And we see there's 8 of them. And whenever we say order doesn't matter, so the probability of 2 boys and 1 girl with order doesn't matter is what? How many of those pathways did we highlight? Well, we have highlighted 1, 2, 3 of them, right? Or down here we can see 1, 2, 3. And when we see it like this, we can see the order they were born, right? And we can tell there's definitely 2 boys in there. So 3 out of those 8 pathways lead me to 2 boys and 1 girl. So 3/8. All right? Okay. So the next thing we're going to do, looking at this right here, I'm just going to take this one a little bit of a step farther, is that we're going to talk about something called a distribution table, probability distribution. You can think of this as a frequency table for probabilities. Okay, that's how I think of it. Okay, probability distribution. Okay, so basically, whenever we do this, we're not going to list these as individual outcomes anymore. So here I have the 8 total outcomes. Instead, it's going to be kind of like this. And what we're going to say here is the final event that has happened. Okay, and I'm going to start with 3 boys, 0 girls. Okay, and this is going to be the frequency. How many times did it happen? And over here, I'm going to put in the probability. And sometimes you'll see some of these, and not all of them. Sometimes they leave out the frequency. You might just have the probability that that will happen. Okay. All right, so let's talk about that. How often did we see 3 boys, no girls? Well, it only happened once, right? One time. The probability that a family of 3 children would have 3 boys is then what? It happens once out of how many pathways? In my head, I hear you 1 in 8. Say 1 in 8. Okay, so that's the first total event that could happen here. All right. Now, next could be, what if it was 2 boys, 1 girl? Now, that's the outcome that we just did, right? Okay, and we said that there were 3 ways that that could happen. Now, think about it this way. We had, this had a 1 in 8 chance. This had a 1 in, everything's got a 1 in 8 chance, right? They're all equally as likely of happening as the others. Okay, it is not unfairly weighted. So these are all equally as likely. So there were 3 of those, but wait a minute, we just said the probability of having 2 boys and 1 girl was 3/8. So that probability over here is 3 out of 8. Well, how in the world did I get there? So hopefully you'll see whenever I'm talking about something like this happening, this is an or statement. That's the way I think about it whenever I do these questions. In an or statement, they are all inclusive. So basically, I want you, if you have boy, boy, girl, boy, boy, girl, or that's 2 boys and 1 girls, right? boy, girl, boy. Okay, that's 2 boys and 1 girl. Or I want you to have girl, boy, boy. Okay, any of these guys, I want you. So whenever that happens, whenever we think, oh, I want this any way that this thing occurs, that's including all of them. I want to include them all. Think to yourself, oh, I'm adding. Okay. So earlier when we had those independent events and we wanted both of those to happen, that was an and statement. I didn't say that earlier, but I should have. So let me go back and add that real quickly. I'm sorry. So let me change this, add this in here. These are and statements. Okay, I'm going back to the first page of notes we had. So basically what I mean is that I want a 3 on the red and I want a 3 on the blue. Okay, that's what we're happening there. I want both of those statements to happen at the same time, right? So whenever I want both of those to happen, oh, okay, we're talking about an and statement. So that was multiplication. But here we're looking at this or statement, and guess what? We added, okay? So that's a different way of thinking about how these outcomes relate to one another, okay? Or these total events, I should say. So what would be the event where I had 1 boy and 2 girls? How many possible different ways does that happen? Well, 1 boy and 2 girls, here's one, girl, girl, boy, girl, girl, or girl, boy, girl. Well, that happens 3 different ways, right? So you can see it here, here, and here. 2 girls, 1 boy. 3 different ways. So what do you think about that probability? How many different paths did we get there? Well, we could get there 3 different pathways, and how many total paths? 8 pathways, so 3 out of 8, 3/8. All right, and the last possible thing we could have done was we could have had 0 boys and 3 girls, right? And in how many of my pathways was that? Just the one, right? 3 girls. So that just happens one way, and that's 1 in 8, okay? If I've done everything correctly, and you can figure out this percentage or that percentage and all that. I'm just going to leave these as fractions, but you can totally figure out their percentage. But if I've done this correctly, then down here at the bottom, I should be able to do a total, okay? And whenever I finish, I'll have 1/8 plus 3/8, that's 4/8, plus 3/8, that's 7/8, plus 1/8, that's 8/8, or 1, or we know 100%, right? If we had changed that into percentages. So this goes back to test 1 where we were doing percentages and stuff like that. And I said, oh, sometimes we just want to leave it with that common denominator. This is one of those times where I want to make sure I have all of my options. So yeah, I'm going to leave it be. I'm not going to mess with it. So there you go. All right. If you wanted to, you could count up your pathways and you could say, oh yeah, there are 8 of these total. 8 paths. Okay, so we're good there. The other thing you can think about here is this thing has a bit of symmetry going through it, this probability distribution. And if it's a nice fair situation, like these gender things are, then a lot of times you'll see this symmetric thing. There was a 1, 3 on the top, and on the bottom, right through here, if I split my table, on the bottom I have a 3, 1. I have a reflection going on, 1/8, 3/8, and then 3/8, 1/8. So you start kind of seeing this, oh, if this is a fair thing, then a lot of times we'll have that happening when we look at our probability distribution tables. Okay? All right. So make sure when you add all those up, they all add up the same. All right. So here we go. I want to know 2 things. And I kind of misspoke a little bit earlier. I think I said whenever we do, it was the very beginning. Sorry. I think I said that, let me make sure. Not dependent on probability of B. Okay. Counting rule says if these events are independent events, then you can multiply P of A times P of B. And I think I just kind of misspoke that a little bit, so let me go back and change that real quickly while I'm thinking about it. They don't necessarily have to be independent events. So let me change these. I'm sorry. If we want both to happen, I may have to remake this video. I'm sorry. Counting rule says if we want both of these events to happen, then you multiply probability of A times probability of B. So I misspoke just a little bit. Okay? All right, let's talk about that independent thing. Okay, we've talked about that my roll of a blue die doesn't depend on the roll of my red die and so on and so forth. Let's talk about a deck of cards. And we're going to do an interesting little situation here. So we're going to say, what's the probability that you pull, and pick your favorite thing, a jack out of a deck of cards. Okay. You replace the card back into the deck. And then you pull another jack out of the deck. What's the probability of that? Okay. Now this one is going to depend on whether it's independent or dependent. So let's think about it. What's the probability that I pull a jack out of a deck of cards? Let's talk about that first. How many jacks are in the deck of cards? Remind me. 4, I hear you saying in my head. I know, I hear a lot of stuff in my head. Okay, and how many cards were there in that whole deck of cards? 52. Okay, so it was a 4 out of 52 chance of pulling that first jack out, right? All right. And then I said, oh, I put that jack back into the deck of cards, right? Okay, so I put him back into the deck of cards, and what? What does that mean? Did that change the probability when I put that jack back into the deck of cards? How many cards are in that deck? 52 still, right? I replaced it. So with replacement, that's what it's called, I didn't change the probability at all. So what's the probability of pulling the second jack? It's still 4 out of 52, right? All right. So I didn't change the probability at all. All right, so whenever, here's the upshot, whenever events are independent, they don't change the probability of the other event happening. Okay. So what that means here, remember we had that definition at the beginning. So what that means here is that when you replace the card, then these are independent events. We don't care. So all we care is, oh, we want a jack and we want another jack. So those probabilities are the same, 4 out of 52 times 4 out of 52. Now you can multiply that. It would be 16 out of 2704. Or you can reduce it first, 1/13 times 1/13. Or you can reduce it at the end. I don't care, however you want to do it. When you end up, you should have 1 out of 169. There's a 1 in 169% chance, okay, probability that I'm going to pull at random a jack, put that jack back in, and then pull another jack, okay? So that's interesting. Now, let's slightly alter this situation. Okay, same thing, but I want to know, what's the probability that you pull a jack keep the card, and then pull another jack? Oh, now we're changing the situation, aren't we? Okay, because I kept the card. Okay, when I keep that card out, let's look at this problem. What's the probability of the first one? Well, the probability of pulling a jack is still 4 out of 52, right? Out of a normal deck of cards that's fair and, you know, don't have extra kings and jokers or aces or whatever. Okay, so that's still 4 out of 52. That doesn't change. But what changes here is that I kept the card. So this is oftentimes called without replacement. Okay, so think about that. And what happens is, because I keep the card, it changes the probability for the next one that I draw. Okay, so let's think about it. Now, how many jacks are in that deck of cards? There were 4, but I kept one of them. So there's only 3 jacks in that deck of cards now, right? And before there were 52 cards, but I kept that jack. So what does that mean for my denominator in the second fraction here? Now there's only 51 cards, right? Okay. So it changes, in this case, both the top and the bottom of this. Okay. So now what? Oh, now I need to look at this and say, oh, it's going to be a little bit bigger. You can go ahead and reduce this sum, for instance. I know this is still 1 out of 13 times 3 out of 51. 3 and 51 will reduce as well. 1 out of 13 times 51 divided by 3 is, oh, we'll go back. Sorry. Got my calculator going, 17. Okay, so now I just multiply across the top and multiply across the bottom. It's 1 in 221. Okay, so it's even less likely once I keep that card, because think about it, there's 1 fewer jacks in the card deck right now. So it's less likely that the second card will also be a jack, basically. So it's only a 3 in 51 chance instead of a 4 in 52 chance. Okay, so the total probability for me to pull both of those and keep that first card, not replace it, and get a jack the second time is only 1 in 221 chances. Now, if I was doing this, I could do a tree diagram for this, and it would be messy, of course, because there's 221 possible outcomes here. So sometimes we're not going to do that kind of thing, right? It doesn't make sense for me to do that. But there are some of these things that are interesting to see the probability. All right. Let me see. In the homework, you might see something like this. A relative frequency probability. Relative frequency probability. Okay, so if you see something like that, then I don't want you to go, what the heck is that talking about? So here's an example of a problem like that, and I just want you to see it and know it's out there. It's not a big deal. I think you guys could probably do it without me even showing you an example, but let me just get it out there. It says a certain river has flooded 4 times over a 2,000 year period. Okay, certain time over a 2,000 year period. What is the probability that the river will flood this year? Okay, now here's the thing. people would say, oh, it only flooded 4 times over a 2,000-year period, so it's 1 in every 500 years. So if it hasn't flooded in the last 500 years, then now's the year. Or if it's flooded 3 years ago, then it's not going to flood this year. That's not entirely true. Okay, there's still a possibility of it flooding this year. It's just very slim possibility. So let's think about that. It is, so the relatively frequency part of this, we are going to do that like we would. Uh-oh. Oh man, I hope it's still recording, so let's see. Sorry, my computer has shut off on me without any advance notice. Yep, okay, still recording, of course. So I'm like, what is going on here? Shoot, shoot, shoot. Okay, so sorry about that. The relative frequency part and the probability tells us, okay, let's set up a proportion here, a ratio, 4 out of 2,000. Ratio, not proportion. That would become 1 out of 500. So there's a 1 in 500 chance, probability, that it's going to flood this year. Okay? So, it doesn't matter. It could have, we don't know. 3 of these floods could have been 3 years in a row. So sometimes people will call this a 500-year flood. Okay, it's not going to flood because it only floods every 500 years. But we have to be a little bit careful. There's still a possibility that it would flood this year. It just may be very unlikely. Okay, so the probability is very low. Now, to go ahead with this, let me say that this is, let me put this in a notation. This is a 0.002. If you were to divide that out, 1 divided by 500, that's the probability. And whenever I go ahead, remember you need to change that to a percentage. If I move that decimal 2 points, 0.2%. So what is that? Let's think about that. It's less than a 1% chance, right? It's very, very slim pickings here. So it's unlikely that it's going to flood. We don't think it'll flood that river this year, but it's not impossible. Now, it's less than a 1% chance, but this isn't 0%, right? So remember, 0 is it will never flood. Okay, it's impossible for it to flood, but that is not what's going on here. So you got to be a little bit careful about that. All right, I want to do a tiny different probability, and then that's probably about it for this particular video. So when we're talking about dice, let's go back to that 20-sided die that I showed you. Remember the the options on that particular die were 1, 2, 3, all the way up to a 19 and a 20, right? There were 20 sides, and they just had consecutive numbers on them. Okay, so there's my probabilities, or I'm sorry, not my probabilities, my options. My possible outcomes. I could roll this 20-sided die, I could get a 1, I could roll it, and I could get a 20, okay? So I just mentioned that 0% means never. So let's just say I have this particular 20-sided die, and it's a fair die, which means I'm just as likely to get a 2 as a 19 or whatever. So the question becomes, what's the probability that I roll this die and I get a 19? Well, there's one 19, and there's 20 sides, right? So it's a 1 in 20 chance. Okay, probability that I roll this die and I get a 3. Well, there's one side with a 3 on it, and there's 20 sides, and so that's a 20-sided thing. Okay, but you might see some weird questions, so I just want to make sure we're prepared that. What's the probability that I'll get an even number? Well, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, or 20. There are 10 of those out of 20, so it's a 1/2 or a 50% probability of getting an even, and that's the same as the probability of getting an odd, by the way. 1, 3, 5, 7, all the way up to 19. There are also 10 of those, or half, 1 out of 10 out of 20, or 1/2. Okay, so that makes sense, but sometimes you might get something like this. What's the probability that I'll get a 30 if these are my possible outcomes? Well, you look at that and you say, well, is 30 one of my outcomes? No. So what's the possibility that I'll get that? Well, there's 0 30s, 20 sides. I do 0 divided by 20. I get a 0. Okay, 0 on top, 0. 0 on bottom is undefined, but 0 on top is 0, so we're good. We're okay. We can figure that one out. 0. So there's a 0% chance. It's never going to happen that I roll this 20-sided die and I get a 30. Okay, so that's what that means. Okay, what about this? What's the probability that I'll get something that is my roll is greater than 10? Let's do that. What's the probability that my roll is greater than 10? Oh, that's weird because it's not a particular answer again. So let's see, that's the 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? All of those are greater than 10. There's 10 of those out of the 20 options, or 1/2. Okay. What's the probability that my roll is greater than 20? Well, it won't be, right? The biggest possible outcome is 20. So that's not going to happen. So that's 0 of those out of 20, or 0. Okay. Here's an interesting one. What's the probability that my roll is less than or equal to 20? Less than or equal to 20. Well, the biggest possible one is 20, right? And I've got equals, so the equals is okay. So that's going to include the 20. And all the rest of these are less than 20, right? So that's 20 outcomes that are 20 or less. Does everybody agree? And how many total possible outcomes was it? 20. So that's a 20 over 20. When I divide that out, I get a 1. Now let's think about that for a second. This one is a 0% probability, which means I am never going to roll that die and get something that's bigger than 20, right? But this one is a 1. Now remember, that's 1.00, and if I move that decimal over to get a percentage, that's a 100% probability. What does that mean? That means I will always, it's always going to be true. There's no doubt about it. Whenever I roll this particular die, I will always get something that is 20 or less. Okay? So that is going to happen for me no matter what. Okay? All right. I think that's probably it for right now. I'm just kind of checking real quickly to make sure I've hit most of the stuff. Let me wrap up this independent-dependent comment. So basically, whenever you see that, if I put the thing back in, then with replacement means those events are totally independent of each other, right? Okay. Okay. With replacement, those things are independent. Without replacement, those things are dependent on each other. Okay? Those results are dependent on each other. But there are also some weird combinations of stuff that happen. So what if you have this and this? What if this happens after I had this first outcome? So later we will talk about that. What about these unusual situations and how's that going to look for us? Okay? All right. Yeah, I think we're okay. All right, I think that's it for this video. I will finish out probability soon. I think we're getting close to it, and then we'll move on to the next set of content. All right, see you later. Let me know if you have questions.